Hello and welcome to our help video on 6C8. In 6C8 we are determining the shapes of molecules by interpreting the Lewis structure and using the valence shell electron pair repulsion theory. On our very first molecule, we are supposed to determine the shape of silicon dioxide and fill out all the various information we have on that molecule on the page underneath silicon dioxide. So here we go. Let's first of all do the Lewis structure for silicon dioxide. There is one silicon with 4 electrons. It's in Roman 4. And there are 2 oxygens, each with 6. It's in Roman 6 for a total of 12. We have 16 electrons to work with. There's our 16 electrons. Silicon starts with 4 electrons. It'll need 4 bonds to get 8. Oxygen starts with 6 electrons. It only needs 2 bonds to get 8. So silicon will be our element or our atom in the middle. That'll be our central atom. And we will now surround it with 8 electrons. So we now have silicon surrounded with 8 valence electrons. Now we'll attach the oxygens. We can place the oxygens wherever there is a lone pair. So we can attach an oxygen right here, and perhaps we could attach an oxygen right here. And now we'll surround the oxygens with 8. So we now have 8 around all the oxygens. Let's count our total electrons and see if it matches up with the 16 that we are allowed. Around each oxygen we have 8, so that's 16 for the 2 oxygens. And then the silicon has 17, 18, 19, 20 total. So we got 20 total electrons here. We're only allowed 16. So what we need to do is begin erasing and then putting electrons in to the bond on the atoms that we erased from. So our rule for erasing is we can erase any electron pair on an atom provided it is attached to another atom that has a pair to replace it. So for instance, this pair right here on top of the silicon. I could erase that pair on top of the silicon and then move any pair from the oxygen. So I could move this pair in, the pair here, pair here. I could move this pair in, this pair in, this pair in. Remember, when we erase, we have to replace the ones we erased with electron pair from an atom that is attached to it, and the pair goes into the bond. So I'll go ahead and erase this yellow pair. And after erasing the yellow pair, we see silicon is down to 6 electrons around it. We need it to satisfy the octet rule with 8. So I can move a pair from any of the oxygens into the bond. I'm choosing to move this pair that I've now highlighted in blue into the bond, and that should return the silicon back to 8 electrons, and it'll keep the oxygen here on the right at 8. 2, 4, 6, 8. Unfortunately, we still have 18 electrons on this molecule. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'll have to erase another pair. Now at this time, if I'm trying to draw the best structure, I wouldn't want to erase any of the pairs from the oxygen on the right. Because if I erase either of those pairs, I would have to replace it with the pair underneath the silicon into the bond, and that would give a triple bond. So I don't want a triple bond oxygen if I can avoid it. It can triple bond, but I don't want to if I can avoid it. The oxygen on the left here is only made a single bond. So I want to go ahead and use the electrons on the oxygen on the left because it can be double bonded. So I certainly could erase this pair on the bottom of the silicon. And I've colored those yellow now. If I want to erase that pair on the bottom of the silicon, I can move any of these pairs from the oxygen in the bond. So I'll go ahead and get rid of these pairs right here. And then I'll pick a pair on the oxygen to move into the bond, perhaps that pair on the top, and I'll go ahead and color those blue. I need to move that blue pair now into the bond because as we can see, silicon only has 2, 4, 6. By moving these into the bond, I would then end up with 8 around the silicon, and each of the oxygens, both the one on the left and the oxygen on the right, would have the 8 that they need. So now it looks like we've got this. Let's double check our electrons. We should have 16 here. 2, 4, 6, 8, 10, 12, 14, 16. Our number of electrons is correct. We've got that correct number on there. So now we can turn this into a Lewis structure by replacing these shared pairs with lines. So for each shared pair, I will place a line. So we should have a double bond between the oxygens and the silicone. So now we have the correct Lewis structure for silicone dioxide. Oxygen prefers 2 bonds, it's made it. Silicone's allowed 4 bonds, it's made it. So everything looks good here. Everything has 8 electrons. We have the Lewis structure, and now it's time to interpret what shape this is. Notice silicone's in Roman 4 the same as carbon is. So carbon dioxide molecule looks like this if you remember doing it. It would make sense that the silicone dioxide molecule would look the same as well. Let's go ahead and interpret the shape now. All right, as we can see, they want us to start interpreting the shape right here where it says start here. And the first thing they want us to count are the total things around the central atom. The central atom here is silicone, and they want us to count how many total things there are around it. If you remember, the B stands for bonded atoms, and the E stands for lone pairs of electrons. When we're counting the bonded atoms, remember we are counting atoms, not bonds. So looking at silicone, our central atom, we have 2 bonded atoms. And then around the silicone, there are no lone pairs. The oxygens have lone pairs around those, but it doesn't influence the shape of this molecule with respect to the silicone. So that's 2 things, 2 bonded atoms and no lone pairs. So now that we know that the total things surrounding the central atom is 2, we can see that this molecule is going to be linear. So I'm just coming straight over here. It's linear. Where did I get that from? Looking on the shape sheet. When the total things on the central atom are 2, it puts it in the linear family. When the total things around the central atom are 2, we are in the linear family, and there's only one molecule type in the linear family, or one shape type in the linear family, and it's linear. So we've got a 2, it's in the linear family. I can come right back here, and I know that I can now mark linear. So with that, we know there is the only one possible. So I went ahead and circled linear as the family shape. It is also the molecule shape because we saw on the shape sheet that it can, if it is linear, there's only one possibility, and that possibility for the molecule's shape is linear. So the shape family is linear, and the name of the shape's linear, and that means it's a 2, 0, which we already learned it is a 2, 0. So I'll put 2 right here. There are 2 bonded atoms around the central atom. There are 2 bonded atoms around the central atom, and there are no lone pairs on the central atom. So I'll go ahead and put no lone pairs. That is a 2, 0. 2 for my B, 0 for my E, which makes sense. There's my 2, 0. I'm linear. It's in the linear family. So we've got that part fixed up. We are in the linear family. So what is the shape formula? It's AB2E0. I'll go ahead and fill that out. So we have AB2E0 as our shape formula. We can double check on the shape sheet to make sure we've got that correct. We go down in the shape sheet. The B is 2, the E is 0. The formula is AB2, which is the same as AB2E0. When you write E0, you don't have to write the E at all. The bond angle is 180. So let's go ahead and write the bond angle in. It is 180. When we look at the shape sheet here, or when we look at the information we're filling out, the bond angles say axial to equatorial, equatorial to equatorial, axial to axial. Well, when we only have 2 atoms, we don't have to worry about all these designations. So I can write 180 in the box underneath it, and I'm good to go. So I just put 180 underneath all of them, but whether it's axial to axial, or equatorial to equatorial, the 2 atoms oppose each other. It's symmetrical when it's linear shaped. And that's where we're going next. When we take a look at where we're going next on this thing, first of all, we want to look, are they the same atoms surrounding the central atom? Well, we have 2 oxygens surrounding the same central atom, so yes, they are the same atom. So I've circled same atom here. When they're the same atom, that means we're heading towards symmetrical if there are no lone pairs. So here's the no lone pairs. I come out of the no lone pairs. If the lone pairs are not 0, I go up this way. If the lone pairs are 0, I go down this way. Well, there are no lone pairs, so I'm going down here. Are they the same atoms surrounding the central atom is a question right there. We already know there are two oxygens and the E equals 0. That makes this molecule symmetrical. So when we have the same atoms, in this case two oxygens surrounding silicone, and there are no lone pairs to bend it into an asymmetrical shape, we know the molecule is symmetrical. When the molecule is symmetrical, it doesn't matter what kind of bonds they have, because if the bonds were polar, they would cancel. They're not polar. Or if the bonds are polar, they would cancel. So it doesn't matter whether the bonds are polar or not. This molecule has to be nonpolar. So I can come straight over here. If I come out of the symmetrical box and follow it up, it takes me straight to a nonpolar molecule. That means there's no net dipole on the molecule. There's no partial positive or partial negative areas anywhere on the molecule. The type of intermolecular force molecules exert when there is no dipole, when there aren't partial charges and partial negatives and partial positives, the only type of intermolecular force they can exert on each other is called a London dispersion force, which we abbreviate LDF. We'll talk more about London dispersion forces later. All right, let's go ahead and double check what else questions we are asked. What's the strongest intermolecular force? It's a nonpolar molecule, so it would be London. This molecule is not ionic. There was no charge on it. It wasn't like SiO2 3 minus. There was no charge. It's not a polar molecule. In order to be a polar molecule, you have to have polar covalent bonds. You have to have perhaps a lone pair on the central atom to distort the shape, or different atoms surrounding the central atom, which we will talk about here as we continue discussing the homework. At this time, though, we'll go ahead and figure out the electronegativity differences. There's a box to fill there. We'll fill that box, and only because it's there to fill. It really won't influence it. This molecule is not polar, whether there's polar bonds or not. So let's go ahead and do electronegativity differences. We'll look them up on an electronegativity table. We need oxygen and silicone. You do have an electronegativity table in the class information section as well as attached to this assignment. Oxygen we can see is 3,5, the second highest of them all, second to fluorine, which is 4,0. The other atom we have on this molecule is 1,8. It is silicon. So we now can figure out the electronegativity differences. Oh, come on. Here we go.